Welcome back to this explainer, where we're going to diagnose exactly why microchips fail. And honestly, look at the absolutely incredible engineering used to save them. You might not realize it, but every single time you fire up your phone or your computer, there is an invisible, microscopic war happening right inside the device. And it's being fought on a battlefield that's literally smaller than a grain of sand. So today, we're going to become microscopic defect detectives. So, what really kills a microchip? Well, in this high-stakes invisible war, defects basically stem from three foundational root causes. We're talking about fluid flow anomalies, which involve issues with the protective underfills, metallurgical dynamics, which center on the tiny solder joints connecting everything, or extreme thermomechanical stress. But before we look at these specific microscopic villains trying to destroy our chips, let's establish the structural foundation of the whole problem. We are talking about flip chip packaging. This is where you literally flip the silicon chip upside down to connect it directly to the board. It's a total marvel of modern engineering where extreme stress meets unbelievable precision. Every single component must be perfectly placed or the entire system just comes crashing down. Okay, let's just dive right into our diagnostic roadmap. We'll start with the anatomy of chip failures, then systematically break down four specific microscopic symptoms: underfill voids, bump bridging, warpage, and ELK delamination. And finally, we'll synthesize the whole shebang into a master diagnostic matrix. Section 1, the anatomy of chip failures and the foundation of stress. To truly grasp these failures, we first have to look at the incredible physical forces these microscopic materials actually endure. And it really all starts with a property known as the coefficient of thermal expansion, or CTE for short. Simply put, as materials heat up during operation or even during manufacturing, they expand. And as they cool, they contract. The catch? Different materials do this at completely different rates. And that leads to a massive mismatch. We've got the rigid silicon die, which expands at a pretty slow rate of roughly 2.6 parts per million per degree Celsius. But it's attached to an organic substrate that expands at 15 to 17 parts per million. Think of it like building a road out of two completely different materials glued together. That massive expansion mismatch creates severe, relentless structural stress that literally tries to tear the chip apart. Section 2, underfill voids and fluid flow anomalies. Let's move on to our first specific microscopic villain, trapped air. So underneath the silicon die, engineers inject a fluid to protect all those tiny connections. But sometimes invisible pockets of air get trapped. These underfill voids act like ticking time bombs. Not only do they weaken the mechanical strength of the chip, but they also create tiny little moisture traps. As the chip heats up and cools down over its life, these voids can lead to dielectric breakdown, which basically means microscopic electrical sparks where they absolutely shouldn't be, or cause the solder to dangerously migrate. Now, how does this air get trapped in the first place? Well, when you have incredibly dense arrays of connecting bumps and very, very low clearance heights, the liquid underfill really struggles to flow cleanly. Uneven fluid fronts crash into each other, swallowing air pockets. Add to that volatile outgassing, where leftover manufacturing residue or absorbed moisture suddenly boils into gas during the curing process, and you've got a perfect recipe for microscopic voids. So how do we actually fight this? Engineers prescribe a very specific three-step treatment plan. First, substrate pre-baking. This eliminates absorbed moisture before the underfill is even applied. Second, they optimize the dispense pattern to an I line or L line. They're literally squeezing the liquid from just one or two edges so the air has a continuous escape route pushed ahead of the fluid. Finally, vacuum-assisted autoclave curing aggressively forces any of those stubborn remaining microvoids to safely collapse under pressure. Section 3, bump bridging and metallurgical dynamics. Our second symptom on this diagnostic journey takes us deep into the realm of hot metals.
The crucial thing to know here is that bump bridging is an unintended short circuit that happens during the extreme heat of the reflow phase. When the metal is liquid, too much solder volume can cause it to bulge out laterally, or dynamic package warpage, or even just a slight misalignment during the delicate pick-and-place process literally squishes adjacent solder joints together. And once they touch and cool, bam, your chip is short-circuited.
To fix this, engineers execute a brilliant structural upgrade. They swap out squishy, fully melting traditional solder bumps for rigid copper pillar bumps. These copper posts are the real heroes here because they don't melt during reflow.
They maintain a strict, rigid standoff height, entirely preventing that lateral solder collapse. And that is absolutely vital for ultrafine pitches under 80 micrometers.
But they don't stop there. Alongside the copper pillars, they tightly optimize the reflow thermal profile, dialing in the exact amount of time the metal spends in a liquid state. They also use precise solder mask-defined pads. Think of these as microscopic stencils that physically restrict the liquid metal from bulging sideways.
Section 4, warpage and non-wet opens. Next up is a massive structural failure mode, and it brings us right back to those core thermomechanical physical forces. Remember that massive CTE mismatch between the silicon and the organic substrate we talked about earlier? Yeah, this is where it causes absolute chaos. Because the layers expand and contract at different rates during temperature swings, modern, ultra-thin substrates literally flex and bow. This violent warping lifts the corner connections right off their pads, completely ripping them apart into what engineers call non-wet opens or head and pillow defects.
The root causes here boil down to severely unbalanced forces. Beyond just the CTE mismatch across core materials, if the copper routing traces aren't perfectly balanced symmetrically across the substrate layers, the whole package is going to warp dramatically under thermal loads. And those thin substrates we use today, they are especially vulnerable to this relentless flexing. The countermeasure here is extreme mechanical restraint and balance. We mitigate this by upgrading to low CTE materials, like glass core substrates. We make absolutely sure the copper trace distribution is perfectly symmetrical, and, perhaps most impressively, engineers attach physical metal stiffener frames around the perimeter of the die to forcefully hold the substrate flat, literally wrestling it into submission during assembly.
Section 5, ELK delamination and extreme stress concentration. Our final defect mode is arguably the most delicate, and it happens deep within the chip itself. So directly beneath the die's active pads are these highly fragile, extra-low K dielectric layers. The rigid solder joints, and especially those stiff copper pillars we just used to fix bump bridging, actually transfer intense thermal cooling shear stress straight into these brittle layers. Because of the distance from neutral point effect, which acts a lot like a crowbar pulling on a nail, this stress brutally concentrates and tears at the outermost corners of large area dies, causing cracking and peeling.
So how on earth do you protect something so fragile? First, you formulate low-stress underfills to absorb the shock. Second, you add compliant interconnect buffer layers made of ductile nickel, gold, or copper. But my absolute favorite solution here? The dummy bump layout. Engineers intentionally place non-electrical, non-functional dummy bumps at the extreme corners of the die. They act as these brilliant sacrificial shock absorbers, taking the brute force of the mechanical stress before it can ever reach the actual functional signal pads. Section 6, the diagnostic matrix. We've examined the microscopic villains and the incredible engineering cures used to fight them. Now, let's synthesize everything. This matrix beautifully summarizes the invisible war we've just been exploring. You can see our 4 defect modes lined up. Notice the inspection tools required to even see this microscopic battlefield. I mean, engineers have to use CSAM, or C-mode scanning acoustic microscopy, just to find trapped air voids and delamination, while relying on 2D and 3D X-rays to spot solder bridging and substrate bowing. But for every single primary cause, human ingenuity has found a precise, engineered mitigation. We demand smaller, faster, and more powerful technology every single day. And it's only made possible by overcoming these immense physical limitations. So what does this all mean for you? Well, the next time your phone gets a little hot in your hand while playing a game or watching a video, just remember, you are holding an active microscopic war zone, and the good guys are winning. Thanks for joining me on this explainer, and keep questioning the microscopic world around you.